Welcome to class of physics. In previous lecture, we have studied about work, power, and energy in terms of line integral. In this class, we are going to study about conservation theorem of energy and work energy theorem. Let's see first conservation theorem of energy. First statement: law of conservation of energy states that the total energy of isolated system remains constant. That is, energy can neither be created nor be destroyed. If energy disappears in one form, it appears in another form in an equivalent amount. So this is a statement of law of conservation of energy. That means we cannot create any kind of energy as well as we cannot destroy any energy, but we can convert one form of energy to another form. Simply, the potential energy can be converted into kinetic energy converted into potential energy, or heat energy can convert it into another form of energy. Okay, so like that, the total energy of the system remains constant. Now we are going to prove this theorem. For that, consider a particle of mass m moves due to applied force F. We are going to apply a force F on a particle which is having mass m. Due to that is going to displaced. When the particle is going to displace, then we say that the work has been done. So dW is the work done by force in displacing the particle through a distance of dr. Then the work done is given by F dot dr. The total work done in displacing the particle from position 1 to position 2, so that is obtained by integrating that small work done. Here there is a particle here. Now we are going to impose the force F on this particle. Due to that, it is going to displace a small displacement dr in time interval dt. So to displace this small distance, the work done is now dw equal to F dot dr. So now this is a position 1, that is initial position. Now this particle is further going to move at a certain position 2. So what is the total work done to move this particle from position 1 to position 2 when we are going to apply force F? For that, we have to integrate this work done. Okay, so then we will get the total work done to displace a particle from position 1 to position 2. So that is we are going to integrating here. Total work done from position 1 to position 2 is integral of dw from 1 to 2. These two are the initial and final positions that we call it as limits. The dw value is F dot dr. According to Newton's laws of motions, the force F equal to ma. F equal to ma. What is A? A is acceleration. So in terms of velocity, this expression can be written as m into dv by dt. So that we can write it as d into mv by dt. So what is product of mass and velocity? It is momentum p. For that, F becomes dp by dt. Here dr is missing, into dr. So that, in other words, we can say that the force is rate of change of momentum. Then this p value is mv. Okay, so d by dt of m into dr. Next, total work done equal to m into, this m is constant, take it as outside, so m into dv by dt into dr by dt into dt. Just we are going to multiply here dt and dividing. For this it is dt into dt. Okay, so the equivalent of this equation is here. Then what is dr by dt? Dr by dt is velocity v. So then this can be written as d by dt of 1 by 2 p square into dt. Okay, here some complication is there, just we have to reform into this form. When you differentiate this term, you will get the previous one. Okay, so that is multiply of 1 by 2. Then total work done is equal to 1 by 2 me square So this integration value becomes 1 by 2 mv square 1 to 2. So here 1 and 2 are the limits. Now substitute these limits, then it becomes 1 by 2 mv2 square minus 1 by 2 mv1 square. So what is this 1 by 2 mv2 square and 1 by 2 mv1 square? So that is kinetic energy. Okay, what is kinetic energy? So kinetic energy is given by the expression 1 by 2 mv square. Okay, if you write here 2, then it is kinetic energy at position 2. If you write 1 here, then it is kinetic energy at position 1. So that this is now becomes T2 and this is T1. Okay. So then what is work done to displace the particle from position 1 to position 2 is T2 minus T1. So that we call it as the work done by the external force is equal to the gain in kinetic energy of the particle. Okay, so here work done is positive, that indicates there is a gain in kinetic energy. So then this only we can write in another form in terms of potential energy. For that, call this equation 1. Now we are going to try to write this work done in terms of potential energy. If force F is conservative, then work done by it around a closed path is 0. Okay. Now a particle is here. If it is moving here, means there is a displacement here, then work is said to be done. If it completes one closed path, then initial and final positions both are the same position, there is no displacement, that we call it as work done is 0. So what is work done? Work done is given by F dot dr is equal to 0. Okay. So that the total work done for a circular path or closed path, that is represented by this circular integral. Okay, this indicates integral. For that, the total work done for one closed path is 0. Circular integral of F dot dr is 0. Here we are going to apply Stokes theorem. According to that Stokes theorem, circular integral F dot dr can be written as this integral, this surface integral. We are going to convert that circle into surface integral. So integral of curl F dot ds is equal to 0. So for you, these two terms are not familiar. Curl F ds is 0. Integration of any quantity 0 means there should be a there we are going to integrate a 0 quantity. Okay, 0 value. So to obtain these conditions, this one should be equal to 0. Okay, what is equal to 0? Curl F should be equal to 0, that is here. Okay, curl F is equal to 0. Again, curl indicates this is an operation. To obtain this equation, curl F equal to 0, so that one I am writing in symbolically. So that curl is represented by this del. Del cross indicates curl. Okay, curl F equal to 0. Again, to obtain this condition, the F should be gradient of some scalar function. Then only the curl F is 0. Gradient of some scalar function means here the gradient again represented by del. If it is curl, then it is del cross. If it is gradient, it is del dot. For that, F is equal to minus of gradient of phi. Okay. So then only curl F is becomes equal to 0. So that gradient is represented by the symbol del. Not delta, it is del, where phi is the scalar function of known as potential energy. Now this is a potential energy term. So that del is known as directional differentiator. Okay. Then phi equal to dou v by dou r. Okay. Not v, it is del phi. Then del phi can be written as dou v by dou r. That means the del value is dou by dou r, the directional differentiator, dou by dou r. But what is f? F is minus of gradient of phi. For that, minus of dou v by dou r. So it is minus of dou v by dou r. Here it is force F equal to minus of gradient of phi. For that, what is gradient of phi? Gradient of phi is dou v by dou r. Now substitute this f value in the integral equations. Okay. So work done is equal to integral of f dot dr. Integral of f dot dr. Here f is force. Now the force value is what? It is minus of dou v by dou r. So in terms of differentiation, we are taking dv by dr. Okay. So again dot dr, it is dr. The limits are position 1 to position 2, 1 to 2. So here dr, the remaining is minus of integral of dv. Okay. So now change the limits. When you change the limits, it will get minus sign. So minus becomes plus. For that, this is from 2 to 1 to dv. Here the integral limits are 1 to 2, but here 2 to 1. So taking minus sign, so minus, here one minus is there, again here one more minus becomes, then it becomes plus. So integration of this is phi. The limits are 2 to 1. Then so when you substitute the limits, then it becomes phi1 minus phi2. So that is here. Work done equal to phi1 minus phi2. Here phi1 and phi2 are the potential energy at point 1 and point 2 respectively. So call this equation 2. This is equation 2. From equation 1, we are going to write the work done in terms of kinetic energy. What is equation 1? Equation 1 is, here I am writing W12 equal to T2 minus T1. Okay. So these two are the kinetic energies, and equation 2 gives in terms of potential energy. So both are the work done to displace the particle from position 1 to position 2. For that, these two equations are equal. So for that, we are going to equate the equation 1 and equation 2. When you are going to equate the equation 1, what is equation 1? Equation 1 is T2 minus T1, that is equal to phi1 minus phi2. Rearrange this equation, then T1 plus V1 equal to T2 plus V2, so that is equal to E. What is T1 plus V1? So that is the sum of kinetic energy and potential energy at position 1, so that is equal to the kinetic energy at position 2 plus potential energy at position 2, so that we call it as the total energy. This total energy is constant. For that, we can say that the total energy of the particle at position 1 is equal to the total energy of the particle at position 2. So total energy of the particle is constant, that we call it as it is conserved. So this is the law of conservation of energy theorem. Next, we are going to derive one more theorem, so that is work energy theorem. The work energy theorem is also similar to this derivation, just a part of this one. Let's discuss that one here. Work energy theorem. Work done by an external force F upon a particle in displacing a particle from position or point 1 to point 2 is defined as W12 equal to integral of F dot dr from position 1 to position 2. According to Newton's laws of motion, F equal to m into dv by dt, and hence F dot dr can be written as, now we are going to write this the F dot dr value. F dot dr is equal to m into dv by dt into dr, because this F value is m into dv by dt. Then m into dv by dt into v into dt. Why you are writing here? Here dr is equal to dr by dt. Okay, I am going to write dr as dr by dt into dt. So this dr by dt value is what? It is velocity. For that, it becomes v into dt. So that one substituting here, m into dv by dt dot v dot v into dt. So again, so this can be simplified as d by dt 1 by 2 v dot v to dt. Here this v is not the part of this d by dt. This is a separate term. But when you include this in differentiator, then this one should also differentiating. For that, we are going to equate this one or balancing. For that, it is 1 by 2 v dot v into dt. So v dot v is v square. This becomes d into 1 by 2 mv square. So So now we get the value of f dot dr. What is f dot dr? F dot dr is d of 1 by 2 mv square, or this can be written as 1 by 2 m into dv square. Okay. So then when you substitute this in this equation, then it becomes W12 work done equal to integral of d of 1 by 2 mv square, limits from 1 to 2. Then when you integrate this one, it becomes 1 by 2 m v2 square minus 1 by 2 m v1 square, the integration of this one. This one is v square, the limits are from 1 to 2. You substitute the limits, then it is 1 by 2 m v2 square minus 1 by 2 m v1 square. What is 1 by 2 m v2 square? It is the kinetic energy at position 2 minus of kinetic energy at position 1. Okay. The scalar quantities 1 by 2 mv square is defined as the kinetic energy. Thus work done by a force acting on a particle appears equal to the change in kinetic energy. So this equation gives the work done is what? It is a change in kinetic energy. So that is W12 is equal to integral of f dot dr, that is equal to T2 minus T1. So this is known as work energy theorem. So what is work energy theorem? The work done by a force acting on a particle appears is equal to the change in kinetic energy. So that we call it as work energy theorem. So for this, the first unit is completes. In next, I am going to post some important questions on these chapters as an assignment. Please work on that. Okay, thank you.